Hello everybody. So, today we will be continuing our discussions on sieve tray distillation columns primarily, and they can be used for absorbers as well. So, we have mainly covered the major portions of the sieve tray. In the last class we had discussed the limiting operations, and after that how to calculate the diameter, calculation of the tower height by calculating the number of theoretical stages using McAptilly method, and then incorporating efficiency and calculating the actual number of trays, and then taking into account the tray spacing and for individual between individual trays, and also the specific tray spacings at the feed tray or the other just above the feed tray, at the top of the column, at the bottom of the column, taking all these spaces into account, how to calculate the tower height, that has also been discussed with you. So, at the moment you know how to calculate the tower height, you know how to calculate the tower diameter. After the diameter was calculated, we also know how to check about the entrainment level, whether the entrainment level is within limits and it is not going to cause flooding by entrainment. So, till this much we have already done, and I had given you a specific problem from where you found out that what are the typical inputs which are there and what are the things which you are generally supposed to estimate or evaluate for a complete design of the column. Most of the things that have been mentioned are common to all types of tray columns. There are certain specific differences. Definitely the sieve tray is the simplest which we are going to which we are discussing at the moment. There will be certain specific additional features for bubble cap tray which will be taken up when the bubble cap tray design will be discussed with you. Now, just to recollect, this was the design illustration, and out of the design illustration more or less how to calculate the tray spacing, the column diameter were already done. More or less what are the what should be these particular ratios, that was also mentioned to you. Normally AA, this is equals to 0.76 of A, then downcomer area ADC, it was mentioned, it is around tentative. Now, after the design is formed up, we may change these little depending on convenience, but these are the tentative things. And as I had already mentioned, the tray it comprises of two calming zones at the inlet of the liquid, at the exit of the liquid, and the remaining area comprises of the active area. Now, today what we will be doing is, once we have decided the tray diameter, now the tray layout, what the tray has, we know that there will be some space left out for the downcomer and the remaining portion is the active area. So, in the active area we need to lay out the holes. Now, for that what are the things we need? We need to find out the diameter of the holes and the arrangement. Remember, mostly in sieve trays the arrangement is a triangular pitch. In bubble cap trays we use both square and triangular pitches, but conventionally in sieve tray we use triangular pitch. So, we need to decide the pitch, we need to decide the hole diameter, we need to decide the number of holes, and then we need to fit the number of holes in the active tray, keeping in mind that certain portions of the active tray are also not available for the punching of holes, because there will be blanking strips if required, otherwise there will be backing strips as well. So, therefore, and once we have decided on the tray layout, next comes the downcomer dynamics and the outlet weir dimensions, etc. It is usually a V notched weir, that is from conventionally it is taken. So, today what I have planned is, we will take this specific problem and we will go step by step in the design, and in the course of designing for this particular specific problem, we will be understanding how to decide upon the tray layout, downcomer dynamics, outlet weir, and then definitely certain checks which we need to do in order to define that the design is fine. Checks are very evident to you. One check is the entrainment check, which we have already discussed in the last class. The other thing is we assume some sort of an approach to flooding. Yesterday I told you we assume around 80 to 85% of flooding. Finally, after the design is there, we just need to see that the flooding limit has not exceeded. If it is less than what we have decided, it is fine, we can go ahead with it. But if it is if after the design we find we have approached closer to flooding, then definitely the diameter has to be changed and the design has to be reworked. The other very important thing for sieve tray is to check for weeping. So, these are the 3 checks that we need, and after the tray layout has been designed, the tray pressure drop has to be checked, which gives you a check for the weeping. And again you remember, in the downcomer dynamics, it is very important to check up the hold up in the downcomer, the liquid hold up in the downcomer. It has to be at least less than half of the tray spacing, so that by any chance the liquid rather the flooding by downcomer choke flooding does not take place. At the same time, the downcomer backup should be sufficient such that no vapor circuiting should take place. These things were discussed. Today, through the design, we are going to find out, or rather we will see how we can exactly estimate these particular parameters. So, with what do we start? We start with the diameter. You are aware of this particular graph which was shown to you, the graph based on which we are going to find out the diameter. So, therefore, here it is already the data are already given to you, the liquid flow rate is given, the vapor flow rate they are given, and the vapor and liquid densities they are also given. And I have also in fact these were the data that were given. Based on that, I have already calculated the volumetric flow rates for your convenience. So, now let us proceed. In this case, we start with assuming T s equals to 450 millimeters, right. So, once T s is assumed, we are in a position to find out FLV. For our case, what is FLV? Based on our liquid flow rate and the vapor flow rates, it is given as, I will just put down the values, so that in case you have done anything wrong, you can check it up also. So, therefore, this gives you something like 0.0425, right. Now, from here if you can find out 0.1, 2, 3, 4. So, you can go up. We have taken the tray spacing as something 1, 2, 3, 4. So, it should be somewhere here, isn't it? So, it should be somewhere here. From there you can find out what is K1 equals to. From here if you go straight, roughly you will find K1 will be equal to roughly 0.0082. Roughly you will be finding this. Okay. Now, once you have found out K1, then in that case we can calculate this, but we have to remember our sigma. What did we have? The sigma was 28.25. Now, I would like to remind you that this particular whole thing, this was rather this graph, it is based on sigma equals to 20 dynes per centimeter. So, therefore, and we assume for our purpose that AO by AA, this is going to be 0.1. So, therefore, we need to correct K1 just for the correction of sigma. We will not introduce any correction for AO by AA. Okay. So, therefore, once we have found out K1, from there we can find out K1 corrected. This is simply 0.0082 into 28.25 by 20 to the power 0.2, right. So, this gives you roughly about 0.088. So, therefore, I have put an additional 0 here. I will just make the correction. Yeah. So, therefore, we get the K1 corrected as 0.088, right. Now, once we have got it, then using this particular equation you can make the substitutions, and from there you will get UFVN to be around 1.4456 meters per second. Now, here we can assume J the approach to flooding to be 85% as I have told you, right. So, once we have assumed that, we can find out UVN. It will just be from that particular basis, it is going to 1.4456 into 0.85, which is going to give you as 1.23 meters per second. So, once this has been calculated, you can find out the net area. The net area, what is it? It's just going to be once you have found this out 1.23, yeah. So, from there you can find out the net area. The net area, it's going to be around say 0.1195 meter square, right. UVN was equal to 1.23, perfect. Now, we know that AN by A, I have already mentioned, this is equals to 0.88. So, from there you can find out A. I can do it here also, we can find out A. Now, this A we find it out, this is going to be around 0.1358 meters square. Now, based on this, we can find out the diameter. So, therefore, if we can find out the diameter in this particular case, more or less we get the diameter as into 0.1358. So, therefore, this gives us the diameter as 0.416 meters, right. Now, if we refer to the standards, we find that roughly the diameter for this particular range, it is taken off to the next higher value for a proper rounding referring to the codes. So, therefore, we assume the diameter to be 450 millimeters. It does not matter if the diameter is little more, vapor velocity will be slightly less. If weeping can be if weeping is respected, we have no problems with this. So, therefore, we take the diameter. Once the diameter is selected, you once more recalculate A and you get A to be 1.59, right. And from here, more or less the weir height, it is always taken as typically a 2-inch weir we assume. So, HW equals to 50 millimeters. LW you can assume it is generally 0.76 D. So, therefore, this is 0.342 meters. You can see, we to start with, I have told you, we assume the diameter of the perforations to be 5 millimeters, which gives, and we assume AO by A to be 0.1 meters. So, from there let us find out the other distributions. So, therefore, based on this diameter, the ADC it is going to be 0.12 into 0.159, which gives us 0.019 meters square. The net area we need to recalculate once more. This comes to as 0.14 meters square, right. So, therefore, we have calculated more or less these things. Now, once these are calculated, the next thing which we need to do is that with this particular thing, let us find out the corrected approaches. So, therefore, all these things more or less we have calculated and we have kept. What's the next thing that we will do? See, the diameter was rounded off. So, with everything we need to check up the corrected vapor velocity and whether the approach to flooding is fine or not. So, therefore, for this particular part we know what is UVN equals to. This is going to be 0.147 by 0.14, which gives you as 1.05 meters per second. And we already know that our UFVN, this was equal to 1.408 meters per second. So, from there we find that J, which is the approach to flooding, UVN by UFVN, this comes to about 72.6%, slightly less, but anyhow it is okay. It is more or less far removed for flooding. So, therefore, we are fine with this. Now, after this, what is the next thing that we would like to do? We would like to check for entrainment. Before we proceed with anything else, we would like to check for entrainment. If you remember that this was the graph that we had taken up for entrainment. we have already calculated FLV 0.425, J we know it is 73% roughly. So, from here if you take it up 0.425 and around 73% flooding, in that particular case you can just check it up, you will get psi it is equal to 0.045. The acceptable limit is given here. So, therefore, this is definitely less than 0.1. So, definitely we can proceed with this particular design, this is fine for us. Just as an additional information, we would like to find out that what is the total amount entrained, that means the total amount entrained for say NL equals to the moles of the liquid. So, what is the total amount entrained if you want to find? Roughly you can find out the total amount entrained, and then you can find out by how much the Murphy tray efficiency has been influenced. To start with, you can assume the Murphy tray efficiency to be something around 0.7 or 70%, and you can calculate the actual. You will find this roughly to be around 66 or 65%. So, it is not very far removed from the Murphy efficiency that you have assumed. If for your tray you can assume a higher Murphy efficiency, definitely you will get a higher E actual. We find that these two are not much removed. So, therefore, this design is okay as far as entrainment is concerned. So, after entrainment, what should be the next thing that we should be checking up? So, therefore, we have the diameter, we have everything. So, now we will go for the tray layout. Now, there are certain thumb rules which are usually followed for the tray layout. I have already told you that since ours is a non-fouling service, we will be assuming, we have already assumed the perforation diameter to be 5 millimeters. Just for you to remember, suppose we have a fouling liquid, or suppose we have liquids which are containing solids. In that case, there is a chance of the perforations getting clogged. Under those particular situations, we would prefer to go for a higher perforation diameter. Again, if we are having vacuum services or we are having systems with low surface tension, then we would be adopting, instead of 5 millimeters, we can go for a 3 millimeters column. For air separation towers, etc., the perforations can be much less, but for our purpose we will go for 5 millimeters diameter 5 millimeters diameter perforations. And remember one thing, that these perforations, they are either made by drilling or they are made by punching. Normally punching is used if the diameter varies between 2.5 and 19 millimeters. When we are making the holes through punching, then the dimension is often decided by the diameter of the punching die. This is something you need to just, it is for you to keep in mind, that the minimum perforation size under that case is limited by the dimension of the punching die, and that depends upon the tray material and the tray thickness. Normally, we adopt either carbon steel or stainless steel materials. So, therefore, there are certain thumb rules, like the perforation size should not be less than sheet thickness for carbon steel, 1.25 times the sheet thickness in case of stainless steel. Based on this, generally the typical perforation size for your stainless steel for different thickness, they are all given: 3.2 millimeters in US standard gauge thickness of 2 millimeters, 4.76 millimeters for a SS tray thickness of 3.6 millimeters, etc. So, based on that also, your perforation diameter can be selected. Depending upon the problem, you will be selecting the perforation size, but conventionally, to start with, we start with a perforation size of 5 millimeters. Now, there is something interesting I would like to tell you before I proceed further. See, the point is, if we go for a perforation size less than 2 to 3 millimeters, we find what is the limiting operation? Uniform gas flow rate through all the holes, because then it is a challenge to ensure that through all the holes the gas is bubbling out uniformly. So, under such a condition, we find that the minimum gas loading, it actually decreases as you increase the perforation size. But if you go for larger perforation sizes, say greater than 2 to 3 millimeters, then Under that condition, the uniformity of gas flow through all the holes is not a deciding factor. On the other hand, liquid weeping becomes the decisive factor. So, therefore, under that condition we find that the minimum gas load, it actually increases with increase in perforation diameter. So, these are the small things that you need to keep in mind. And also along with that, once the hole diameter has been fixed, then next we come to fix the pitch. Now, the pitch conventionally, again to start with, you can use this particular pitch, and once the pitch and diameter are fixed, we can fix the number of holes per meter square of the net active area. When it is a triangular pitch, then from geometry we know that this is the total number of holes. Now, you can do one thing, you can decide the perforation size, you can decide on the pitch, and then you can calculate the number of holes and try to accommodate the number of holes. We can also go a little different. We know that AO by A, we have assumed it to be 0.1, right. So, that the total number of total area occupied by all the holes, you can easily find out from this AO, right. Now, once you know this, you know the area of each hole. From here you can find the number of holes. Once you have found the number of holes, then from this formula you can find out the P. And then you see whether the P, it is falling, more or less it is falling within this particular range, or it is closely obeying this particular range. If that is admissible, we can proceed with it, or else we have to go for a lower pitch or higher pitch, and we have to adjust accordingly. So, let us see if we go around with the tray layout, then in that case, for what do we have in this particular case? DO, this is equals to 5 millimeters. AO, we have already calculated, this is 0.01208 meters square. So, from here you can calculate the number of holes. What will be the number of holes from here you get? It is nothing but 0.01208 divided by pi by 4 into 0.005 square. One thing you need to remember, consistency of units. This is where the students often in a hurry, they make a mistake and then the problem starts. So, from here you get something like 615.23, we take it as 616 holes, right. We know what is the end wastage area. I have already told you it is around 50 to 100 millimeters. So, therefore, let us start with the minimum, so that we have the maximum amount of the active area. So, this is 50 millimeters width. So, therefore, so you can find this out, what this is going to be. This is going to be this into d by 2 plus d by 2 minus 0.05. The rim, I am calculating the area of the rim, into 0.05. So, from here you can calculate, this is going to be a 0.0314 meter square, right. And then therefore, what is the total AO net that we say, area for punching holes? So, what is this particular area, which is nothing but AO tray? If you remember, this was equals to A minus 2 ADC minus A end wastage minus A backing strips, if you remember. So, therefore, you can keep on substituting all of these. This is pi by 4 into 0.45 square and minus this 2 into 0.0121. In this particular way, the end is wastage area, we have already calculated 0.0314 minus this backing strips. If we assume that the backing strips part I had mixed, more or less the backing strips also there are certain, I had told in the last class, yeah, more or less I think 75 millimeters to 50 millimeters width of backing strip if we take. So, therefore, we will be getting around say 0.15 into pi by 4 into 0.45 square. So, with overall you get the total AO area as 0.0656 meter square. So, if we consider a triangular pitch, then in that case we find that what will be the pitch for corresponding to this particular AO tray. If you calculate this out, you will be getting this is 0.0656 using the formula that I have shown you. This will be equal to 2 into 10 to the power 6 by root 3 NO into 0.656. This whole thing root over. So, therefore, from here we get the pitch is roughly equals to 11.1 millimeters, which is almost equal to 2 DO. So, therefore, we take this up and we find that this is fine. Now, we can take up the calming zone of 25 millimeters. So, therefore, we get the total calming zone and we consider one particular backing strip. Okay. So, we have considered in this particular case, we consider a calming zone of 25 millimeters. So, therefore, you can find out the calming zone, total area of the calming zone. It will be around 0.0171 meter square. This will be the total calming zone in one particular tray. You can consider one particular backing strip and which is 15 millimeters wide. I have shown you and accordingly we have done it. So, in total what we have here, we are having 616 holes and this has been accommodated in a triangular pitch where the pitch is twice the diameter. Fine. So, next after this, what is the next thing that we will be doing? Once this is done, then we will be going for calculating the tray pressure drop. Now, the tray, what will be the tray pressure drop? You tell me on the tray what is there? There is a liquid level. What is the liquid level? It will naturally be equal to the height here HW plus the height over the weir, which is equals to HOW. Along with that, what will be there? There will be some particular head loss as the vapor is flowing through these particular perforations. Now, we have to remember that the liquid which is flowing over HW and HOW, that is aerated. It is not an unaerated pure liquid mixture. So, therefore, the equivalent height, if you find, this will be the total liquid height multiplied or corrected with an aeration factor. Now, this particular aeration factor, normally it is given by an empirical correlation in terms of the vapor factor based on the active area. So, therefore, remember one thing, that whenever you are using such correlations, these correlations, they are since they are derived from experiments or from standard practices, it is very important that you keep the units in mind. So, therefore, if you can calculate beta in this particular case and then you know HW, you know HOW. So, therefore, you can calculate the total operating liquid seal at the tray outlet in terms of the clear liquid height. In order to calculate the head loss, again there is an empirical formula. This formula you find that the head loss, naturally it will be depending upon the vapor flow through the perforations. All these heads, they are given in millimeters of liquid, you need to remember. So, in order to find out HO, you need to find out the vapor velocity through the perforations corresponding to HO. So, this gives you the vapor velocity. AO, you know how to find out AO. So, therefore, if you substitute all of these, then you can find out, you will be in a position to find out HO and all this, HO, HW, HOW. HW, as I have told, it is typically 50 millimeters. For finding out HO, you need UVO, which is there. You also need CO, which is sort of it's equivalent to an orifice coefficient. CO is again given by this particular empirical correlation, where the factor M can be obtained if you know the tray thickness to hole diameter ratio. So, with all this, we find that we are in a position to find out the tray pressure drop. Just certain checks you have to do, that when we are calculating FVA, it is important to find out that FVA lies in this particular range, because based on this the relationship for beta has been done. So, you can start these particular things and you will find that the value of UVA that you get, that will be equal to 1.22 meters per second. FVA you will be getting as something like 2.188, which is definitely it is less than 3.05. So, therefore, you can use up this particular beta here. This beta, if you calculate from here, then you will be getting the beta as something like 0.592, from where you can find out the tray pressure drop, and this particular tray pressure drop you will be getting this as this this is going to be 50.303, the HO that we have calculated, plus the beta was 0.592 and this was 50 plus 10.736, which gives us roughly something like 86.26 millimeters. Well, after this, what is the next thing that we are going to do? Once this is done, the next thing that we will be doing is that we need to check for weeping. Now, you tell me under what conditions you will be getting weeping. Naturally, you will be getting weeping when you find that the vapor velocity is much less as compared to the liquid velocity, or in other words, the head loss due to vapor plus the force due to the liquid surface tension, that has to be greater than this particular situation. Only under that condition, when this is satisfied, then weeping does not occur. Now, how to calculate the maximum liquid depth that can be sustained by surface tension? You can get this from this particular equation. You can calculate and you can find out that this particular H sigma, the H sigma value you can just calculate and you can see for yourself. This will be something around 0.103 millimeters. You can check it out, and HO we have already calculated, and so therefore, most of the values they are calculated here. If you can just substitute them, then you will find that more or less your particular condition that is satisfied. So, therefore, from here you can find out the condition of weeping. Now, when you are finding the condition of weeping, there are certain things which are important for you to know. First thing is that weeping need not occur over the entire tray at one time. It can occur at certain sections of the tray. So, therefore, the condition of weeping is obtained by this equation or this equation depending upon AO by AA. So, for our case, this is the thing which is applicable. So, therefore, what you need to know, based on whatever data we have calculated, you need to find out, you need to use this equation, and you will find that this equation will be satisfied for your particular case. The other thing that we need to find out is, either you have to find out whether the head is sufficient to hold the liquid, or else you can find out the minimum design vapor velocity from the holes to prevent weeping, and find whether your actual vapor velocity it is higher than the minimum or not. The minimum vapor velocity can be found out again from some empirical equations, where we find that this is expressed in terms of a constant K2, where K2 can be obtained from here. Again, there are certain criteria for which, by which you can find out K2 when HLO conforms to certain conditions. Well, so therefore, if you check it up, you will find that HLO here, just check up, this will be 60.736 millimeters. So, therefore, it is obeying here. From there, if you find out UVO mean, you will find this is equal to 6.734 meters per second. Well, and so from there, if you find, you will find that more or less this complies to your case. Now after this, what is left after this, you tell me? The next thing which is left is that the liquid gradient across the tray. You know that the liquid gradient, it should not be too high. Now, this liquid gradient, it poses a greater problem for bubble cap tray. In this particular case, you just need to check if the gradient if it is less than 19 millimeters or 0.75 inches. Only if it is greater than this, then only it has to be taken into consideration. Generally, for sieve tray columns, we do not have this. So, how to calculate this delta? For calculating the delta, this is the standard formula, where this is the friction factor, L path is the total path of the liquid. All these formula are laid down. You just need to substitute the values and you have to do. The width of the downcomer, it is the same for both cases. So, for you it is d minus 2 WDC, and then this is the hydraulic radius of the liquid path. For here also you know all the things. LF is given by this equation, HLO you have already found out. So, therefore, you can find out RH in this particular case. Remember one thing, here all units are in meters. So, therefore, you can find out the friction factor as a function of Reynolds number, just like you do in other different fluid flow problems. Reynolds number can be found out from this equation, and here in this particular factor you have got a term C. This term C can be obtained as a function of the height over wear. We have taken this, so for us C is this. So, once all these things are substituted, and you are supposed to check delta. Do it for yourself. For your case, we will find delta is about some millimeters, 7-8 millimeters or something even lesser than that. So, you need not have to bother. In case it would not have been, it would have been greater, then what we do? We would have tried to see that certain holes could have been blanked. One small thing I had missed, I would just like to mention that if suppose your entrainment factor would have been greater than 0.1, then in that case the pressure drop which you have calculated, the head loss due to vapor flow that you are calculating, this was just for vapor flow, but if the psi is higher, then in that case a liquid vapor mixture would come, and for that case your HO should have been calculated from this formula. For your case, that is not required at all. So, next what we have, the downcomer dynamics. This is similar to for all tray columns. What are the things in the downcomer that you need, you tell me? First thing, you need to find out this particular backup. What is this backup equals to? It will be the H tray here and plus the height of the wear as well as the height of the liquid over the wear, plus the delta, plus the pressure drop which the liquid encounters when it tries to flow through this opening and enter this particular tray. Now, from here what is the height of liquid over the wear? This we can find out from something like the Francis formula. Here in this particular case, if you find out, you will find that HOW for your particular case, this is given as, let me just see where I have calculated this particular HOW. Yeah, from here I have just find out the HOW, it will be around I believe it should not be more than 10.736 or some millimeters, just check it up. The HDC pressure drop, you can find it out from here, where the HDC pressure drop, it is primarily due to your QL by 1000 dA. Where have I put it? No, it is here itself. So, therefore, yeah, this one. So, therefore, the HDC pressure drop you can calculate, you will be getting this as 0.1417 millimeters, and these are all known to you. Delta also you have calculated. So, you can substitute all of these, more or less you will be getting something like about 0.138 millimeters or 0.137 millimeters something, which is definitely less than your half of tray spacing. So, therefore, it is fine for you. The next thing, one thing you need to remember here, that more or less from here the HLDC you have calculated, the actual downcomer backup will maybe something more than that. Why? Because in reality in the downcomer a frothy mixture comes. So, if there is a lot of froth, then to calculate the actual downcomer backup, you need to consider this particular system factors. For our case, more or less we can consider SF to be around 0.85 and calculate the actual downcomer backup. Anyhow, that we will find that that will also be less than half of the tray spacing. So, once we have calculated those things, the next thing is the residence time in the downcomer. Now, it is important to see that the residence time lies between 3 to 7 seconds. So, for the residence time you can calculate, you can find this will be equal to 0.135. This is for the HLDC that I have got 3.8 into 10 to the power minus 4. More or less you get this as 6.786 seconds. So, therefore, this lies between 3 to 7 seconds. So, therefore, this is fine for us. The next thing is the downcomer velocity. The downcomer velocity also you calculate, more or less you will be getting this roughly around 0.02 meters per second. So, therefore, the recommended range of velocities is this. So, more or less we find that this is close, and so therefore, we can comply by this. It is sufficiently below the choking level. So, once everything has been calculated, then in that case generally we show the layout in the way I have shown you. Here you need to fill up all the relevant dimensions. The tray inside dimension was say 450 millimeters, hole size 5 millimeters, pitch was taken around 10 millimeters, number of holes was 616. We assume that all the holes were active, and we did not have to blank anything. The plate material, downcomer material we have selected, the tray spacing was 450 millimeters, the tray thickness was 3 millimeters, roughly the tray pressure drop was around 86-87 millimeters, the downcomer area was roughly around 0.019 meters square. So, this is the way in which a sieve tray, complete sieve tray design is specified. So, with this we complete the design of sieve tray. We have discussed how to find out the diameter, the tray layout, the downcomer dynamics, and the checks are to check that we have sufficient downcomer liquid backup, and we have checked against flooding, weeping, and flooding with entrainment flooding as well as downcomer choke flooding. So, with this we have completed. You can try out the problem yourself and see whether the values are tallying with it. Only thing that you need to do is to keep the units in mind, because most of the equations and relations that we have used, they are empirical in nature. Thank you so much.